Hello, everybody. So now it's time to speak about overcoming the obstacles to achieve higher temperatures than 100 degrees Celsius with a hydrocarbon-based heat pump. I'm Søren Korsbæk, product manager for Sabro, that is part of Johnson Controls. And just to briefly mention a little bit about Johnson Controls, we are close to being 140 years old and have close to 100,000 employees around the world. So we are globally based and have a broader presence. But these heat pumps that we are to talk about today, they are primarily focused on the European market. So starting on, why heat pumps? 2 years ago, our politicians made this Repower EU in order to double the rate of heat pumps across Europe to switch from fossil fuels away from that to electrify our heating purposes here. And for that we need heat pumps, and heat pumps primarily from us up until now has only been focusing up to 90 degrees Celsius. So we want to raise the bar, raise the temperature, and thereby help our customers transition away from fossil fuels to a cleaner technology. So yeah, currently what we do out of Sabro is ammonia-based heat pumps, and as you can see here, we have 3 different pressure ranges that is able to deliver 56 degrees Celsius for low pressure and medium pressure 52 bar and 60 bar design up to 90 degrees Celsius on ammonia. What we are bringing here closely starting of next year will be based on butane and isobutane, so it has 2 different refrigerants that we can switch around. So one isobutane up to 110 degrees Celsius and butane up to 125. And what obstacles have we seen here by shifting over to newer refrigerants? Equalization during standstill has been a new point that we need to have a much better understanding of, same as condensation of gases in unwanted places. That's a different challenge. And then superheat is important, and there are some differences here between ammonia and how hydrocarbons work. And then the ATEX, is that a necessity? That's often a question that we get with these highly flammable refrigerants. So I just mentioned it briefly about that, what can be done, how to mitigate that, and how we have done it. Equalization. Since we go into even higher temperatures than we have had before, and the temperature difference between normal operation or standstill temperatures around 20 degrees Celsius and operating is even higher, it's also easier to get condensation of liquid in different places on the equipment. So of course we need to be aware of that and take measures according to that, because we can see on butane at 20 degrees that's roughly 1 bar, and at discharge temperature around 120 that's around 21 bars. So that's a large pressure difference. So during standstill, it can easily condensate in unwanted places if we don't have insulated enough or have heated piping and so on to make sure that it only occurs in places that we want it to happen. Furthermore, superheat is important, as we all know, to protect the compressor. What we've seen on ammonia is that what we're used to there is we get a lot of discharge superheat during the compression cycle. So if we compress from 0 Kelvin superheat directly up, we get around 56 degrees Kelvin in superheat on the discharge side. So that's quite easy on ammonia, but on hydrocarbons here, take the example of isobutane. If we just compress directly again from 0 Kelvin superheat, then we get around 8% liquid out of the compressor after the compression cycle. And we don't want that. We want to protect the compressor, of course. So we need to add some suction gas superheat to get at least a small amount of superheat on the discharge side as well. So by adding around 20 Kelvin, just as an example here, on the suction side, then we can get around 10 Kelvin of superheat on the discharge side, and thereby moving the compression cycle out of the two-phase area and protect the compressor and have a stable heat pump. And there's a small but also notable COP improvement by doing this. Is if we use an internal heat exchanger to deliver that superheat on the suction side, we also get an improvement on the COP around 8%. So during normal operation, we can use this internal heat exchanger between the evaporator and the condenser to deliver this suction gas superheat. That's all well and fine, but it can be a bit tricky to deliver superheat during initial startup because we haven't raised the pressure or the temperature on the discharge side. So if we have a look over here, we can see on initial startup we could have, for example, these temperatures, and just pressing the start button, we increase the pressure on the discharge side of the compressor a small amount, but the condenser and the liquid inside the condenser is still quite cold. It hasn't been heated up, so that makes it difficult to create suction gas superheat over here. So we need to do something else, and that's what us as manufacturers needs to be aware of when we build heat pumps on hydrocarbons. So there are a lot of possibilities that can be done to make sure that that's working. We have found our way, people might find another way. And all these considerations we have solved on our heat pumps. This heat pump here, we call it the HyTemp. It's being released to market here in the beginning of next year. It's a highly standardized and modular heat pump design where our customers can configure the correct product to them, specifying the different sizes of heat exchangers to their specific need. And as I mentioned earlier, we have these two refrigerants that we can shift around to optimize the best capacity and the temperature that they want. There's a small capacity penalty, you could say, by shifting over to butane compared to isobutane. It's around 30% drop in capacity, so that's why we have the different refrigerants to switch between. And that's why we don't just stick with butane, because of that capacity drop. This heat pump will be able to deliver up to 1,200 kilowatt a month, and it's based on a low pressure refrigerant. These hydrocarbons. That also means that we can utilize our SMC compressor and extend our service intervals to a longer. We'll have longer service intervals on these heat pumps compared to our ammonia-based heat pumps. It has a fairly small footprint, 6.5 meters by 1 meter and 2 meters in height. So I believe we have a quite good product here. Ta-da! The compressor was the SMC compressor that we're using. We have two different versions of that, an S version and an L version. That's the stroke length, that is the difference. So the S version can ramp up to 1800 RPM and have a minimum turn down to 28%. And that means we have a fairly large capacity range that we can deliver to our customers. Our L version can ramp up to 1500 RPM and has a minimum turn down of 33%. So it has a slightly lower capacity regulation band, but also has a slightly higher COP value by running with lower RPM. That's the difference that you can see over here. So it's always a balance, trying to figure out what you want. But that's some of the things that we can help talk with customers or clients about finding the right solution for them. Yeah, you can see you get a slightly boosted in overall COP by having an L version that runs on lower RPMs. And it's available both in 4, 6, 8, and 12, and 16-cylinder version, so there's a broad range of capacities that we can deliver to our customer. Regarding ATEX, is that a necessity, or does all components need to be ATEX approved when we are dealing with Class A3 refrigerants? Not necessarily. It depends on how you design the unit and do your risk analysis on it. If we have a look on EN 378 and EN 697, that opens up possibilities to design different enclosures or different machinery rooms, so you don't need full ATEX components on the complete heat pump and still have a safe, reliable solution. You can do it by either an ventilated enclosure, where you keep a constant ventilation flow inside the enclosure, and thereby make sure that cannot cause any hazardous zones inside. Or you can design it as a machinery room, as it's called in EN 378, and have a gas detector start up the ventilation, and thereby making it safe inside the machinery room. So there are different ways of doing it. So no, you don't need a full ATEX deployment of components on these refrigerants. Just a minor detail for our current customers that are using ammonia, you cannot place the two refrigerant in the same machinery room because of the thermodynamic properties of the different refrigerants. Ammonia is lighter than ambient air, so that rises to the top inside the room. So you need to take the exhaust out of the room from the top, and the hydrocarbons are heavier than the ambient air, so that flows to the floor, and thereby you need to take the exhaust of the machinery room at the floor level. But all of this we have covered with our enclosures that is available with our new heat pump. So there's both an EX ventilator, carrying on all the safeties regarding that, and gas detectors as well, and sirens and blinks according to the standard. So you can buy a complete plug-and-play safe solution from us with these refrigerants. So where can these new heat pumps be used and for which applications? Of course, you could use it in a hot pressurized water circuit, so you simply raise the pressure on this secondary side of the heat pump to be able to keep the water in a liquid phase. And here's an example of that. With our largest compressor, we can deliver close to 900 megawatt by delivering 105 degrees Celsius. And that can save our customer roughly 600 tons of CO2 equivalent per year. Another example could be producing indirect steam. So keeping an artificially high pressure up on this side of the condenser, keeping that high enough so we don't boil the water, and dropping it afterwards into a flash tank, and thereby taking steam out of a flash tank to the heating consumer. So delivering a steam solution in that way. There's another example here where you can see the same compressor again, but due to the higher temperature that we are delivering here, the capacity is 600 kilowatt with a COP of 3.2. And you save, our customer for this application will save around 250 tons of CO2 equivalent per year. If you need higher temperatures than that, then what we're able to do with this product, you could add on the discharge side of the flash tank, you could add a steam compressor there to raise the pressure even higher. So there's a way to go even higher. So I think this product would fill in for most applications at our customers. It's important to know that all our heat pumps are tested, both from a functional perspective, but also the performance is tested in our end-of-line test center. So all data and performance are tested and according to the original offer. So there should be no surprises for our customers, and customers are always welcome to be a part of the capacity test at our facility. So that was it from my side, and then just want to let you know that we have a booth in Hall 7 at location 240, so please come and talk to us if you want to know more about our products. And some of my colleagues are also having other presentations around here at Tilvenza, so please come and hear their presentation as well. There are also a few, some of them are already covered, but there are a few left for tomorrow. But thank you for your time.
Yes. Yeah.